In accordance with the customs of this university, I open the ceremony with the following words. Spiritus Sancti gratio illuminat senset e corda nostra. Please be seated. So welcome everybody. We're going to witness the defense of the thesis of Taha Selim. So the candidate will first give a short introduction to his work, and then he will be questioned by this committee. So without further ado, I now give the floor to the candidate for the degree of doctor.
Yeah, thanks, Rector. So with the permission of the doctorate board, in order to obtain the degree of doctor from Radboud University Nijmegen, I would like to defend in public my dissertation entitled Quantum Dynamics of Molecules in Space, Theoretical Studies and Efficient Computational Methods for Collision-Induced Row Vibrational Transition Rates in Molecules. We all curious about the formation of planets, and so do astrochemists as well. And the planets, according to current astronomical models, are formed out of protoplanetary disks. Those are interstellar molecular clouds that came out of a sequence that is started by the collapse of gigantic molecular clouds called nebula, under the influence of their own gravitational field, until the central part of their core becomes dense and hot enough to start nuclear fusion. And in this case, a new star is born. Around this young star, the remnant materials start to fall inward. And due to the conservation of angular momentum, the whole system starts to spin and rotate very fast, leading to flattening the molecular cloud and gives a birth for a protoplanetary disk. These contain the ingredients for planet formation. Understanding the chemistry of protoplanetary disks gives an idea to understand planet formation, but also the evolution of solar systems. If we zoom in here on one of protoplanetary disks, in particular in the outer parts, we can see presence of key molecules like carbon monoxide, carbon dioxide, hydrogen cyanide, water, acetylene, and methane. These key molecules play a significant role in the chemistry of the disks. Their spectra also can be used to infer the physical and the chemical conditions in these interstellar media. Thanks to the phenomenal and powerful capabilities of the James Webb Space Telescope, this is a recent telescope that can observe, thanks to the powerful near and the mid-infrared observational capabilities, it can observe the rotational vibrational transitions in these key molecules. Here is an example of a recorded spectra from James Webb. We see it here represented by the black line. And the model of this spectra is represented by this red filling, which composed of emission lines from these key molecules. And after the modeling, we can see that these key molecules have been identified in this spectra. We see here, for example, acetylene. We see here also hydrogen cyanide, and we see water. And in several cases, we see vibrational transitions happen in different vibrational modes of carbon dioxide. Even with these powerful capabilities of James Webb, the transitions in the bend mode of the isotope of carbon dioxide has been identified. So the spectra contains a lot of information. However, modeling the spectra is not easy because these key molecules are present in environments where they are not in thermodynamic equilibrium, which means that the level population or the number of particles at a particular quantum state cannot be described slowly by Boltzmann statistics at a given temperature, which means that for radiative transfer models and astrochemical models, astrochemists need two main inputs for their models. So the spectra can be induced by radiative processes, which means that due to the escaped radiation and then we have stimulated and the spontaneous emissions. The efficiency of this process is described by Einstein coefficients. Also, the spectra can be induced due to molecular excitation and de-excitation, and the efficiency of these are described by collision rates. And of course, these are the two main inputs. Einstein coefficients are mainly known for small systems in the literature. However, collision rate coefficients aren't, and for that, we need to compute them, and the collision rates are obtained from quantum mechanical calculations. And hence, it came the motivation for the Dutch astrochemistry network, in particular the gas phase, where in the first phase, astrochemists needed the raw vibrational collision rates induced in carbon monoxide by collisions with hydrogen atom. Carbon monoxide is a very important molecule. It is the second abundant molecule in the universe, so it's more abundant after the hydrogen molecule. And after the success of the first phase, we came to the second phase where it concerns the carbon dioxide. And we wanted to compute the raw vibrational collision rates in carbon dioxides induced by collisions with helium. Carbon dioxide is a very important molecule. It was found in several protoplanetary disks, but also in our solar system planets like Venus, and some moons like Jupiter's moon Europa, and also the atmosphere of exoplanets. And for that, CO2 or carbon dioxide is a linear molecule. It has 3 vibrational levels. 2 modes of them are infrared active. We see here on the right these modes. They are numbered as the following. So the first mode is a symmetric stretch mode, where the 2 oxygens move in opposite direction while the carbon doesn't. And this is labeled by nu1. And the second mode is the bending mode, where the molecule bends in the plane. And of course, since this molecule is degenerate, we describe the rotation of the plane by the quantum number LV. The third mode is the asymmetric stretch, where the 2 oxygens goes in one direction and the carbon goes in the other. And this is labeled by nu3. The first mode, the symmetric stretch, is not IR active. However, the other modes, bending and asymmetric, are infrared active. The overall rotation of the molecule is described by the quantum number J. And here we describe the total quantum state. This is actually how it's also done in the calculations. So when we came to the PhD project, we come to these 2 main challenges considering CO2. First, we need to develop the theoretical formalism and the codes to enable the calculations. Secondly, we need also to develop efficient procedures to reduce the computational complexity. And here is an example for the computational complexity. To do one calculation involving the symmetric stretch and the 2 energy levels in the vibrational mode. So, for example, here we can have the initial and the final. Typically, we solve equations like this. And in one single calculation, if we have the number of coupled equations around 100, it takes about half a second. If we have 300, it takes about 4 seconds. But typically now it scales quite quickly up. And then if we have 5,000 or more, it's almost 6,600 seconds, and so on. So we see that the computational complexity is proportional to the third power of the number of coupled equations. So in this PhD work, we have developed the theoretical formalisms and the codes to calculate the rates of collision-induced raw vibrational transitions of CO2 with helium atoms. And to enable also this calculation, we have already computed accurate potential energy surfaces for all modes using high level of theory. And here an example of the potential contour plots of potential energy surface of the bend mode. And the quality of the potentials were quite good. And then when we computed the collision rates, we can see here, this is an example for the bend collision rates. And the blue line is the experimental data, and the theory and the experiments, they are matching quite well. With this, we came to paving the way with the knowledge that we have developed and also the methods to compute the collision rates of Fermi resonance, But also this knowledge and the formalism and codes can be extended to other molecules as well, in particular the linear organic molecules, which are the main interest of the phase 3 of the DAN network. And these molecules like hydrogen cyanide, acetylene, diacetylene, and cyanoacetylene. This I give as a floor to the rector. Yeah, thanks. Having presented this summary of my dissertation, I return the floor to the rector. Yeah.
Thank you, dear candidate. That means we can now start with questioning. But before we start, I would like to welcome the external candidates in the committee. We're always honored that there are people from outside also taking part in these defenses. And that is in the corona, Professor Van Dishoek from the University from Leiden and Professor Tennyson from University College London. And online on Zoom, yes, you can also see them, I see. It's Professor Liek from the Université de Rennes and Dr. Laureau from the Catholic University in Leuven. So I now give the floor to Professor Waters to start the questioning.
Thank you, Mr. Chairman. Dear candidate, it's really a pleasure and an honor to address you as the first opponent here today in your thesis defense. And I would like to take this opportunity to congratulate you with a really impressive thesis, which addresses a very important topic in astrochemistry. That is to derive accurate and reliable collisional cross-sections and collision rates for abundant molecules that we find in space and that we would like to analyze with the data that we now have. And you have focused on a particularly interesting molecule, carbon dioxide, and looked at the collisions with the helium atom. And these calculations are really crucial because if we want to extract meaningful information from the data we get from these very expensive telescopes, then the calculations you have done are really a very important ingredient without which we really wouldn't be able to extract the correct information. So a lot of astronomers just do something if they don't have the data that you have been calculating, and they just go ahead and derive things, and with the data that you are now providing to the community, they will be able to do that in a much more robust and reliable fashion. So I think the entire community should be really grateful that you have spent a significant part of your scientific life now making these calculations. So thank you very much for that. Having said that, I think it's now time to come to a few questions that I would like to ask you to clarify this. I'm certainly not an expert on this, the hardcore theory that you have developed in your thesis, but nevertheless, I did come across some questions that I would like to ask you now. And the first question is about the coupled channel method that you use a lot, in fact, throughout your thesis. And you present this as basically the gold standard of your methodology. And then, of course, the question that comes to mind is, how sure are you that the CC method is actually the method that you can actually use as a benchmark against which you compare all the other calculations? And then I looked in your thesis and I found a figure, which is actually also what you just showed in chapter 4, figure 411, where you compare these CC calculations for some collision cross-sections to observations, and then you say, oh, it agrees quite nicely. But if you look carefully, then there are subtle effects in the data that don't seem to be quite reproduced by your theoretical calculations. So I was wondering, can you say something about how reliable are the CC calculations themselves? Do you have any idea how to benchmark them? Do you use any approximations in getting to these results? And are these numerical in nature or otherwise limiting the accuracy? Thank you.
Dear opponent, thanks very much for the nice introduction and for the compliment. Thanks for the questions. So regarding the CC method or the coupled channels, this is an exact method that's based on first principle. So it's developed from the Schrödinger equation, and coupled channel is a time-independent solution of Schrödinger equation. So the method starts from first principle, so it's exact. However, sometimes in general, the variation in the results might come from the quality of calculated potentials. So that's also a significant part of the calculations, the way that the molecules are interacting and their shape, and also the level of theory that's involved in the calculation. In most cases, in general, I mean, not in particular for CO2, but in general, developing also much better potentials using coupled channels gives better results. So the formalism is exact, but the terms that are included depending on the precision that we need. Like if we need, for example, sometimes to include extra coupling terms that might also enhance the comparison to certain experimental results or observational studies, and this is to be included, or sometimes the level of approximation. And due to any increase that is done in adding, for example, more equations, like more bases involving more states or so, that adds to the total computational complexity of the calculations. And hence, the motivation comes for the approximations, to use approximations. And we have been tested during the work several approximations, and also use them to compose efficient procedures to obtain, for example, in this particular case, the rotational vibrational transitions that are relevant to astrochemistry, because there's a lot of molecules, and we need a reliable, efficient method that's still an approximation, but can provide good quality result for the astronomical models. Having said that, in principle, the CC or the coupled channels is an exact method, and the approximation is used to reduce the computational complexity. Then we come to the quality of the results. Typically, the quality that comes from CC, depending on the comparison to experimental results or observation. And when we come to this point, sometimes if the level of approximation or the number of terms that are included is not enough, adding more still within the CC would enhance the results and make it comparable to the experimental or observational data. So still the formalism exact, but it depends on how much we include in the expression, and of course the level of approximation, and also the details of the potential.
Thank you. But would you then say that the limitation is really, for instance, in the accurate knowledge of these equipotential surfaces, or in the number of terms that you need to include in your numerical setup in order to get to the required accuracy? And how do you actually know that you have reached this required accuracy?
Yeah, in principle, yes, that's the idea. And we have also, for example, in the Bend case, an example, because it has a degenerate modes, then the theoretical formalism has to include, for example, the vibrational angular momentum term, and this is what gives the correct doublet of Fermi resonance, for example, or that will give the correct transitions, and also the correct states that will be living and the states that will be omitted. So that's including more precise terms and accurate potentials. That indeed will enhance the results.
Okay, thank you. So maybe I can then move on.
A short question and a short answer.
The next question, which is also again a general question that relates to the shapes of the rate coefficient curves as a function of temperature that you finally derive. You first get the cross sections, and then you get to the rate coefficients. For instance, on page 80, you show figures 310 and 311. You show some examples of those rate coefficient curves as a function of temperature. And I just was curious because they have a general shape, right? They rise at very low temperatures, and then they have a dip, a minimum, and then they increase again to higher temperatures. And can you sort of qualitatively, intuitively maybe, although with quantum mechanics you always have to be careful about intuition, explain the general shape of those curves. And also I try to find some systematics in figures 3, 10 and 11, because you show them for different J values. I thought I saw systematics, but then I gave up in the end. So maybe you can also say something. Is there any systematic trend as a function of J in these different curves? So those are the two questions. Thank you.
Yeah, the opponent, thanks very much for the questions. Honored indeed. So that's indeed a nice question. So if we come to the figures, we see these are state-to-state rate coefficients. For example, for lower transition from lower initial states, that will be mostly higher at low temperature because of the resonance. The resonances contribute to the collision rates. And then they start to, of course, we have a dip because that's where the resonance regime starts to decay down, and then the collision is really about exciting and de-exciting the vibrational part of the molecule. And then we see this rise again in the trend of the collision rates. And if we sum all of these, for example, if we sum state to state from a particular initial state to all final states, that's the vibrational quenching, we get this typical like a known rate coefficient or quenching figure, where we have the at the low collision energies we have, or the low temperatures, we have the contribution of the rates, and then we are sort of contribution of the resonances, and we are sort of after that hitting the vibrations, then we have this dip, and we come growing higher after that. So that's and the other details depending also on the coupling, and yeah, there is fine details in the coupling. And also, how the anisotropy of the short range and so on. But this is a like typical trend that comes if we have the quenching rates. We get sort of by summing all of this, we get sort of this nicely growing collision rate curve.
Okay, thank you very much.
Okay, then I give the floor to Professor Tennyson.
Dear candidate, I enjoyed very much reading your thesis. I learnt some very interesting things from it. And I have to say, I love the Netherlands habit of producing these small books of theses. I have a nice row of them on my shelf, and this will take an honourable position next to the other ones on my row. I don't know any other country that does it like this, and it's really nice. So I'd like to ask you a couple of questions. I was very interested with the comparison with the vibrational close coupling results of Clary, which was sort of the previous results everyone was using, because sometimes you got excellent agreement, and on other times you completely disagreed. And I'd like just if you could explain why sometimes their method, the cruder method from Clary, works with your higher class method, and sometimes it completely disagrees with it.
Yeah, so dear opponent, thanks very much. Honored for the questions. So the VCC IOS, or vibrational close coupling infinite order sudden, that's so sometimes it gives nice results and sometimes it doesn't, and it has been used extensively in literature. And we cannot say, for example, that we understand it in full. However, we have some indications where it can work and where it doesn't. And in the bend chapter, chapter 4, we, for example, we artificially varied the vibrational frequency, and then that means increasing the energy gap and reducing it. And we found that using the same potential, the same everything is the same, apart from just only changing the vibrational frequency. VCC IOS gives nice results around. Almost a 667 wave number and in this vicinity, and if we go lower and higher, the differences becomes very high, and it doesn't agree with the coupled channels for the vibrational quenching anymore. So that's one thing. The second thing is also the details of the potential. So depending on the anisotropy of the potential, in particular the short range, the VCC IOS might work or not. So this is what we didn't have time to investigate it further, but we had these two main indicators about when it's really can work.
So if you're going to do a new system, say acetylene, which is even more complicated because it's more atoms, is it possible to predict when the VCC will be sufficient, or you need to actually make the comparison to know whether it works or not?
Yeah, so thanks very much for the question. So, so typically, comparison brings new insights about how the method is working. But if we have, for example, to take into consideration that using depending on the energy gap, that might work or not. So if the energy gap is high. So, in particular for higher modes, then mostly VCIS wouldn't work. But for lower modes, it can give a fair agreement, I would say. Yeah.
Okay, thank you. So, a different topic. I'm a great lover of doing my calculations body fixed because life is easier. You transform to space fixed. Why do you do that?
Thanks for the question. We can, of course, do the calculation in space fixed or body fixed. They are all equivalent. Just only when we do it in body fixed, there is much more optimization in calculating potential as a potential matrix and so on. And then the reason for that is in body fixed, still we have these helicity quantum numbers, this simultaneous projection of the monomer and complex angular operators on the z-axis. This one doesn't die because still they are mixed. However, if we transform it to space fixed, we have the centrifugal part that goes with the L quantum number, and those become a good quantum number in the long range. So we don't really need to propagate very far. It's the centrifugal dies, and then in the long range, L is a good quantum number, so it could be used in the asymptotic matching to obtain the scattering wave functions. But this is not the case in body fixed unless we really propagate really far in this.
Okay, thank you. One last question. My colleague already asked you about temperature dependence. You extrapolate the temperature dependence. How reliable do you think your extrapolation of the temperature dependence is? Because from my experience, that's something that's quite difficult to do correctly.
Yeah. So thanks very much for the question. That's indeed a nice one. So the reliability, of course, we have to compare to experimental data, but usually when we have enough grid in the integrand, what is left, it's a small part just to because of the integrand just decays, but asymptotically with the temperature. So we do a fit to extrapolate that and make the tail much larger, so we can extrapolate to higher temperatures. I would say it can give fair agreement, but to know exactly how it's reliable, we need to really calculate at higher collision energies and compare in this. So typically in astrochemistry model, if the precision was it depends on the precision that's required also. If it's really an experimental, then maybe we will calculate it. But for astrochemical models, it might be enough or good enough for the model.
Okay, thank you.
Thank you, Professor Tennyson. And I now give the floor to Professor van Dishoek.
Waarde kandidaat, dear candidate. My compliments as well on this beautiful thesis. I too like the cover. I'm still wondering what this is exactly that I'm seeing there. Maybe you can explain that as well. But I want to also add sort of my words to those of Professor Waters. How important the work is that you are doing for astronomers, because as one of my colleagues used to say, if we didn't have the chemists and the physicists who really understand molecular processes and can calculate them, the numbers that go in it, we would be, as astronomers, sort of playing tennis without a net. On the other hand, you would also show very nicely in your thesis how the astrochemical questions actually drive you to develop new methods. And I think your new, fast, accurate methods will be a game changer, especially for your successor, who is going to calculate several more molecules. So let's start actually with a broad question, general question. More than 300 molecules have been observed in space. Why is CO2 a particularly important molecule to study, and how do we think that it's actually formed in space?
Thanks very much, dear opponent. Thanks very much for the questions and for the compliment. So that's indeed a nice question. So CO2 is present, in all papers I read, they discover more and more traces of CO2. For example, it has been found, for example, in planets in our solar system, but also in these interstellar media, like in protoplanetary disks, and also atmospheric of exoplanets. And there is about the formation of it. I'm not particularly sure, but there is also talks where I've attended where there is also big question about how from CO, for example, we can get to CO2 and some clouds. And there is also a lot of models to predict that and assume. So I'm not sure which one has been concluded about the formation of it. This is what I know about it.
So do we see CO2 only in the gas phase in space?
No, I think we see it also in different forms, also on ice and in other forms as well.
So that is one way of forming it. The other one is indeed with reactions, in this case probably with OH, CO with OH being dominant. That's good. So we can observe it now. You showed the beautiful first JWST spectrum. We have many more beautiful spectra now. But that spectrum in figure 1.5 contains not just the 1 to 0 bending mode, but it also contains these hot bands from other between vibrationally excited states. Can you say a few words on how these levels could be populated? And I'm thinking in particular in connection with your figure 5.1 in first figure in chapter 5.
Thanks very much for the question. 5.1. Yes. So first, regarding the first figure about 1.5, that's indeed there is several peaks corresponding to different transitions that happening in different vibrational modes. Typically, because this is not, those molecules now are coming from places where they are not in thermodynamic equilibrium, so they could be excited by emission, but also by collisions and due to, for example, low density and so on. So also molecular excitation and the excitation would play a role in this. So this could be these are the two potential main sources to do these excitations and those transitions. And in figure 5.1, that's now we have those transitions. We have, for example, the allowed transitions for CO2 from between different vibrational states. But also representing which one corresponded to which optical band and light.
So do you think that these vibration-excited states are primarily populated by collisions, or is there another way of getting to those, looking at this figure, of populating those various levels?
Yeah, so it could, of course, transitions can, there is combination effect. It could be also induced by vibration, but also by emissions that escaped from the star there, and cause also this depending on the mode. So that also could be excited and excited by radiation as well. And there's always trade-off between how these are excited by radiation and how these are excited by collisions.
Exactly. So I was indeed aiming for the radiative pumping that we now also do see in some environments. And one of the transitions that could be very important there is the asymmetric stretch, the nu3. At 4.3 microns. Yet we hardly ever see that particular transition. Why would we see the bending mode but not the asymmetric stretching mode?
So thanks for the question. From what I can conclude from the work that we have done is if the collision rates of the asymmetric stretch, the quenching from asymmetric to the ground state is the collision rate is really very small, so the efficiency is not that high. But for the bend is very high one, so that would correspond to the probability of how much we can find, for example, transitions in the bend comparing to the asymmetric transitions. And this, for example, we have computed these rate coefficients in several places in the thesis and compared, for example, the asymmetric, symmetric bend mode.
Okay, if I can add still.
A short question, yes.
So I would like to go more to the methods, and especially I come from quantum chemistry, so I like potential energy services. And in chapter 2, you compute a 3D service. In chapter 5, a 5-dimensional service. So what drove you to add the extra 2 dimensions? Why did you need those?
Yeah, thanks very much for the question. In the first case, in chapter 2, it's involving the symmetric stretch. So we need a 3D potential in a case that we need coordinate first to describe the motion in plane where the high helium is approaching the carbon dioxide. And also we have the vibration, and this is the third in Jacobi coordinate. This will be the third coordinate, and this is done on the normal coordinate Q2. So in that case, we need a 3-dimensional potential to describe the interaction involving also the stretch when the molecule stretches and compresses, and that also has some effect on the accuracy of the vibrational quenching and the symmetric stretch. When we came to chapter 5, because now the main aim of the chapter to include the Fermi resonance part, we had the symmetric stretch and the bend mode. So we had to include the normal coordinate, the one that describes the vibration of carbon dioxide on the symmetric stretch, and the one on the bend. So we have 2 coordinates, and of course the bend also, because it's degenerate, it happens in plane, so that plane in principle can rotate. So that rotation will give the rise to we have the phi angle, and then in that sense we have 5-dimensional potential energy surface. Q1, Q2 are theta, are the radial coordinate theta and the phi.
Right. So did you do a comparison for the symmetric stretching mode between using the 3D and 5D potentials? Did it make any difference for the modes that you could calculate with both potentials?
So we did some calculation, but of course when we did the details of the potential, it changed a bit. So that's one thing, because we used F12 method in this potential, and this is for historical reason, because we were using, for example, mid-bond function and then F12. This is the first thing. So in principle, they give a qualitative agreement, but then just as the tiny details would be considering the vibrational frequency that we have used in the earlier work. We have used a vibrational frequency that a bit different slightly different from the one we used in chapter 5. So we get almost the cross sections are close, but tiny details.
Well, close. So this comes back to the question about the accuracy. Would you put more effort if you want ultimate accuracy? Would you put more effort into calculating more potential energy points, more accurate potential energy points? Maybe the fitting of it, or would you put it into the dynamics? So which of these two is now sort of mostly determining the accuracy of the results?
So for the raw vibrational transitions, we use already CCSDT, a good level of theory with a good basis set, and we have also used this bond-centered functions. So that one gives a pretty nice agreement, especially for the anisotropy of the short range. So we have good results in that In the bend, we did more tests in the bend because it's more observable and more needed. So we tested even the grid propagating further, computing more points, how many points we need, for example, for the phi. And from that, we obtained really good, accurate potential energy surface where we compared it to the experimental rates. So depending, for example, on whether we have experimental results to compare to, and then we do more effort to study everything and see how.
Right, it does help to have some experimental results to compare with. Thank you very much.
Okay, thank you. So now we move online, and I pass things over to Professor Leek. Can you hear and see us?
Yes, do you hear me?
Yes.
Thank you. So, dear candidate, I first apologize for not being able to come to Nijmegen for your PhD defense. But in parallel, I would like to congratulate you for this impressive work. We know that computing collisional data for raw vibrational excitation is a very challenging task, and it seems that you overcome it. So, really, it's an impressive work, and congratulations for that. So I have a first question related to your presentation and your manuscript. You said that collisional data are not known. So I guess you mean that they have to be calculated. But presently there are collisional data for more than 50 molecules. So can you tell us a bit about the state of the art of collisional data? What is available, what is not? What are the current limits of such calculations?
So, dear opponent, thanks very much for your words and for the questions. Yeah, indeed, what I meant is that not all of them are calculated. From the literature, I will just project the answer on carbon dioxide. So carbon dioxide also had collision rates that were computed in literature, but using, for example, some approximated methods like VCC-IOS, and the old works of Clary, and some old also potential, for example, using the SCCF method. And those rates might be enough at this time, but what still for a small molecule, but what we do now is really we try a full exact method, and also was much better potential energy surfaces. And then we see, for example, that we can obtain collision rates much better. The second thing is the state-to-state. So in literature, state-to-state weren't hardly computed for raw vibrational, also due to the computational limits that were present in the past. But nowadays, we also can provide total quenching and state-to-state collision rates as well. So we can add more, and this is also helpful for the high-resolution spectra that's also obtained and so on.
Okay, thank you. Another question is, you mentioned that there are other important molecules in protoplanetary disk, HCN, HC3N, or C2H2. Do you think that the method you have developed can be used to get data for this molecule? Because you have no symmetry, so they are heavier than yours. So do you think it can be used, and what will be the limit of the method you used and developed?
So thanks very much for the question. So in principle, the knowledge and the methods can be extrapolated and be used for these linear organic molecules. The only thing, so they could be extended easily. Like for example, the one that's combined distorted wave, Born approximation, and nearest neighboring Coriolis coupling. That's basically embedded in the way that we treat the coupling and the formalism of the body fixed. So that could be extended easily. Having symmetry in the calculation is good because it's much more saving in computational time. But if in cases if it is not present, then those methods will help significantly reduce the computational time. So instead of propagating a full CC matrix, we're propagating separate blocks and then obtain cross-section and sum them, that will add saving to the calculation.
Okay. Another question related to the bending excitation. You may know that the excitation of water by helium and H2 has been studied by Thierry Stockland co-worker. So he developed a close coupling approach, and I wanted to know if it's the same than yours or if there is any differences.
So thanks very much for the question. So that will be now the task of my successor, indeed. Of course, in astrochemistry, they need mostly for more modes. So we look at what, of course, have been computed, and then what is still missing, and then maybe compute in that. But this will be also the future prospect of my PhD successor to explore, indeed.
Okay, and the last question, the rate coefficients you have found are weak compared to pure rotational excitation, 10 to minus 13, 10 to minus 14. So we know that high density will be required for collisional excitation to be efficient. And you know if such situation occur in protoplanetary disk, or if collisional excitation play a weak role on the excitation?
Thanks for the question. If I understood it correctly, so the excitation and de-excitation, in particular for the formalism that we are using, they are related to one another. So we can compute them. This is from a computational perspective. But for the interstellar media, if it is density is high, then Boltzmann distribution will be dominant, and then mostly the level population in every, for example, an energy state can be determined by Boltzmann average.
So thank you and congratulations again for your work.
Thank you. We stay online, and I give the floor to Dr. Leroux.
Thank you. Can you hear me?
Yes.
Yes, perfect. Dear candidates, first, let me also apologize for not being there in person. And then second, let me join my colleagues in congratulating you for this very nice work, this important and timely work. I enjoyed reading the thesis a lot. Although if I may provide a small criticism, I think in the different chapters you always provide an introduction that is a little bit repeating the overall introduction, but still it's a very nice piece of work. Now, continuing what my colleague just asked, and about non-LTE effects in protoplanetary disks, you don't really explain the range of temperatures that you need to investigate. So can you say a few words about that? What are the physical conditions, and especially in terms of temperature? You go up to 300K, sometimes 500. Is that enough? Do you need more?
Dear opponent, thanks very much for your words and for the questions. So in principle, in some modes, we needed to provide typically for the models collision rates up to the room temperature, and this is what we have done. But sometimes, the models require more temperature, and this is why we go to 500, and maybe we need to provide more. So what we provided now is a way to test the methods that we have developed, but also the potentials, and give data up to 300 or 500. But in case some models might require higher, maybe than 500, then we just need to compute those and extend those as well.
Yeah, thank you. Now I have a question about the quantum chemistry methods. You already discussed it a little bit, especially the fact that you don't really give explanations for your choice of methods. So in one case, for example, when you compute the vibrational frequency of CO2, you use DCSDT with a quadruple zeta basis set. To compute the 3D potential, you use triple zeta basis set. And then in chapter 5, you use the explicitly correlated method, F12, with the triple zeta basis set. So what guided your choice? Did you do any benchmarks? Can you comment on that?
Thanks very much for the question. So the first choice came from the history and works of our research group in Nijmegen. Because the research group also were doing extensive work for ultra cold collisions. So in that sense, using TCSDT combined with good basis set like AVTZ or AVQZ and higher, that were good for ultra cold collisions and also size consistent. But in chapter 5, we tried different level of theory combining CCSDT with F12. So it includes also the dispersion, but also it is very accurate and very efficient, combined with FETZ basis set. However, it is not size consistent, but for this particular use case or the particular applications that we have in computing raw vibrational transitions, including the Fermi doublet, that method is very accurate for this application. So this is why we started with this, and then we changed it because there was a bit of inheritance work in the beginning.
Okay, but so you did not do any benchmarks in terms of comparing, for example, with the complete basis set calculations or things like that?
So we did.
Is this correct?
No, we did in the beginning. We have. So now I get the question much better. So we have done already this. We have done a conversion test where we see when we can get good interaction energies, and we have tried also the Q and higher bases, and then we found that AVTZ with the center mid bond functions, that one gives very good potential comparing to higher bases. So this is why we had that initial choice.
Yeah. Okay. Then in terms of the dynamics, you focus on raw vibrational transitions. Did you also look at pure rotational transitions in excited vibrational levels and compare them to what happens in the ground vibrational level, for example?
Thanks for the question. We have done this for internal discussions, but we didn't publish them because also there is also differences in the convergence details and the parameters. So that would require further investigation in this. We have explored, for example, the pure rotational transition. Sometimes if we have a higher initial state in, for example, V1 in the bend, how it behaves comparing to how it transients to lower initial states. That we have explored, but we didn't just consider them for publication or anything, because the main motivation was the raw vibrational transitions, and also there were a lot of works on this.
But if you want to do astrochemical modeling, you also need, I assume, pure rotational rate coefficients, right? So it's important to look at whether there are differences between those pure rotational transitions in excited vibrational levels and in ground vibrational levels, isn't it?
So thanks. Of course, it depends on the project. We were tasked more with raw vibrational transitions, because this were much harder in terms of including for polyatomic, in terms of including the different vibrational modes. So we had to work the theory about including normal coordinates and so on for this. But it could be helpful if it's needed to be computed indeed. Yeah.
All right. And then a last question. During your talk, you mentioned other molecules such as HCN, XC3N, C2H2. Yeah. And in the manuscript, you comment on the fact that the behavior of collisions by H2 is quite different than with helium as far as vibrational excitation is concerned. So do you think going forward it's more important to investigate other molecules with helium, or to do, for example, CO2, but now with H2?
Thanks very much for the question. So, of course, helium is a good benchmark to make sure that one molecule was done properly. I mean, like CO2, now we have all knowledge about, for example, the couplings that giving rise to the Fermi resonance and so on. So considering H2 or going to higher molecule, other molecules, that would depend on the application indeed. But CO2 is hydrogen molecules that will be indeed interesting to explore.
But the rate coefficients are quite different for H2 than for helium. Do you agree? This is not.
Yeah, and also H2 can absorb energy as well. I mean, in some particular cases.
Exactly. Yeah.
That will be now. Depend on the Dan 3 project what kind of rates they need and to compute there.
Okay. Thank you very much.
Thank you. So we return to the corona, and I give the floor to Professor van der Meerakker.
Thank you. So, dear candidate, I also really would like to warmly congratulate you with this beautiful thesis. I've been privileged to follow your PhD trajectory already for quite long, because you were sharing an office with one of my students, and every time I came to the office to ask Mathieu how he was doing, I quite regularly found you and Mathieu engaged in, well, very deep scientific discussions, but also many other discussions related to the problems in the world, cryptocurrency and whatnot. And I think you really had a good partner together in the office, and that really helped you during your PhD. I'm an experimentalist, so I read the thesis with great interest, but also some parts, it's not really my expertise to go into that depth in the theory. But when I started reading on page 12, I noticed, and we have been discussing this already with a few of my colleagues here, you call the Koppel-Channes quantum method exact. Now, there's always a little bit of a problem when you call something exact. And if I discuss our experiments with my theoretical colleagues, and if there's a discrepancy between experiment and theory, I always make the joke that experiment is always exact, right? If done properly, the experiment never lies. So if there's a problem, it must be in the theory. And of course, we experimentalists, if we are uncertain about something, we put an error bar on our data points. Now, you have been discussing, and you toned already down your premise that the quantum method is exact, and you have been discussing that with colleagues, but you don't put an error bar on any of your CC results in your thesis. So can you become a little bit more quantitative of how exact should I interpret your results?
Yeah. Dear opponent, thanks very much for your words and your kind congratulations. Thanks for the question. So that's indeed, it's maybe it's other way around in theory. Still, the belief that the theory should be exact, but that's also a separate discussion indeed. Qualitatively, the quality of the method, it depends, of course, on the sensitivity of instruments that are used and what kind of effects are being considered. And for example, in this work, it was considered raw vibrational transitions. So that's mainly happening not in the long range, but in the short range. So we didn't really require to have a accurate long range for the potential with different parts of the theory to correct for that. In that sense, we made all of these choices that led to those results. And we made a comparison with an experiment that was done, and the experiment had the error bar indeed, and we were within on the points. So it means that for these particular choices and the formalism, that was good and give excellent agreement with this experimental data. But maybe in the future, something might come up, and then more to explore, or maybe for pure rotations, because long range will play an important part. Then more accurate potential should be calculated, and the theory become much better.
Okay. Yeah, it was nice to see that you have this comparison with experimental data, these were rates, and I also really like the comment by my colleague, Professor Van Dishoek, who said experiments are needed. So as an experimentalist, let me ask you, what kind of data would you need from us experimentalists to actually test best your new theory?
So thanks very much for this nice question. That's also the concluding part of the work. So if we have an accurate collision rates that are measured experimentally, then we can compare our computed collision rates with this, and then for sure we know the quality of the results, how it looks like. For example, in the comparison that we have done, we had an excellent agreement, but maybe with recent experiments, collision rates might be a bit different, or then we...
So sorry, may I interrupt you? So you like collision rates? Yeah, rather than cross sections.
Cross sections or collision rates that will be good to compare, so we would know immediately how the quality, for example, of the potential and the terms that we included, how they are compared, and the probe the underlying physics that led to these experimental measurements.
Okay. Let me go in a little bit more depth in one of your theories that you used, one of the methods that you used. So if we look at figure 3.8 and 3.9 on page 78 and 79. I was a bit struck by this plot because, first of all, in your CC calculations, you see these beautiful resonances. And actually, I was hoping that you would mention that you want us to measure those resonances because that would really test, I think, part of your theories. But of course, that will be very difficult. But you compare your CC results with a number of other methods, and in particular, I'd like to focus on those NNCC methods. You have two of them, one where you only take the integer L's into account, and the other one the non-integer L's. And you also have already a plot before that is on page 74, figure 3.3, where you see actually both methods at high energies, they are giving the same results, but then at very low energies it completely goes wrong, right? There's even a difference of 7 orders of magnitude between the two when you approach the ultra-cold Wigner regime. And that makes sense. You also describe that in your text, because if you do not have the even L's, of course you miss out on the S waves, and that is governing the Wigner regime at the ultra-low temperatures. But if I now look at figure 3.8 and 3.9, I see if you start off in the V equals 1, J equals 0 state, both methods, they are exactly the same, whereas if you start from J equals 6, they actually do start differing.
So yeah, we'll answer shortly. Thanks very much for the question. So the reason for that is when we have for this particular method, it depends on how where we truncate this helicity quantum number in body fixed, this omega quantum number, and having low initial state in this method would mean that it is really exact comparing to coupled channels, because this small block that's propagated in this case is identical to coupled state because the J equals 0. So it means that this 3x3 small block is almost like exact like CC. But when we go to higher initial state J equals 6, then here we see differences because now the approximation is playing a role where we have to propagate several times and different blocks in order to probe and use these tricks either of matching with integer L or non-integer L. And this is where the variation comes in.
Thank you.
Okay. Defense is hereby concluded. I give the floor once again to the candidate.
So, having defended my dissertation to the best of my ability, I would like to thank you, Rector, and you, my supervisors, and all of you who have honored this ceremony with their presence.
The doctoral examination board retreats for its deliberations.
That was a bit a bunch of questions.
On behalf of the doctorate board of Radboud University Nijmegen, we have decided to award you the degree of doctor. I invite Professor Groenenboom to discharge the task assigned on him.
With the power entrusted by law to the doctorate board, I hereby confer upon you, Taha Ibrahim Mohammed Salim, born in Cairo, the title of Doctor from Radboud University Nijmegen, to which are attached all the associated legal and customary rights and duties with respect to academia and society. As proof thereof, I present you with this doctoral diploma signed by the rector and the doctoral thesis supervisors.
So we can all sit down and then. Oh, yeah.
Dear Dr. Salim, dear Taha, it is a great pleasure to be the first to address you with your new title. I also want to congratulate your wife, Asma, and your parents. I also want to congratulate all the friends and family that you acknowledged in your thesis who help you on this journey to this point. I think it is also appropriate for me to congratulate right now and to also thank your second supervisor present here, Professor Ad van der Avoird. We all worked closely together from the start of the project. It has been quite a journey. We started together a little over 7 years ago. It was, I think, about a year after Lai Song finished her thesis in the round 1 of the Dutch Astrochemistry Network, which you showed in your short introduction, in your 10-minute presentation. And yes, we had worked on the collisions of carbon monoxide, CO molecule, and yeah, you proceeded to study the collisions of CO2. So one way to put it, we worked 7 years to add 1 atom. Of course, there are other ways to look at it, right? 1 atom, 3 degrees of freedom, and it is a quantum treatment. And quantum mechanics just has this thing that it scales badly. Quantum mechanics is hard, and we are a theory group. We all know this. I would also argue that it was all well worth it, since we were playing maybe a small part in a great scientific endeavor, really, right? The James Webb Telescope to study the astronomical environments, and that project took like 30 years. Well, delays like 14 years somewhere in between that. And when you think about it that way, the quantum chemical calculation supporting this study of the universe, started in the 70s, half a century ago. So we had decades to really see it coming, that this was an interesting thing to study for quantum chemists. And in the end, I think we were the first to get there. So when you look at it that way, something to be proud of, maybe. Of course, there were people explicitly seeing how important this would be, and it's great, of course, to have a driving force of this all here today with us, Professor van Dishoek from Leiden, who was, really a driving force in all of this and motivating this study. So I want to thank her. A big thank you to Professor van Dishoek here. Of course, in hindsight, it's fun to paint ourselves as being part in a historic scientific endeavor and all, but of course, reality at some times and moments is just plain miserable, right? I mean, it's not easy to get here, and you had to deal with many issues, or several issues at the time. Of course, there was COVID, we have all experience with that, how that interferes with things. yeah, for you the extra complication was, right, I was just when, you know, the isolation started, I was planning to go on a 3-month sabbatical in the US. I just made it out of the country when it was still possible, but then I stayed away for half a year. And you know that doesn't help to work on a project like this. Yeah, in the end, when your contract ended, you had a lot of results. You had done a lot of work, but you know things were not published. And you know until the last tiny bug, that last minus sign in the code is finished, right? You in quantum mechanics, you just don't have anything yet. Now at that point, of course, there are other things than minus signs to worry because you also have to live, right? You have to, you know, you have to get a job, and I think you know this is the point where I can talk, you know, a little bit about your character. We have all seen you here today, and everyone who knows you, you know, you're a super friendly guy and smiling, and that is how you approach things. Not just when things are fun, but also when things are hard. This is how you just keep going. You have that smile, and okay, this is what needs to be done. We do that, and you looked around, yeah, to solve also the problem of, you know, earning some money and of course fighting the immigration, the IND service, to keep them at bay. Now, yeah. You had a lot of experience with that, right? From the beginning, you spent hours at the City Hall and in The Hague explaining bureaucrats how to fix the mess they made. But you know, you also managed those parts of the journey. You were also able to take advantage of this small window of opportunity after COVID, when there was actually money for education. You know, luxury we since have maybe lost, but you were able to yeah, find a job at the university where you could, you know, at one side stay here, earn some money, and keep working on your thesis. Now, of course, from that point on, you have more than one thing to worry about. So, of course, then time goes very fast. But still, I admire how you kept on going and actually managed. And today we see the results. You found a job after that. You're working, and that is, I think, really interesting, in the Amsterdam University of Applied Sciences in quantum computing. And a very advanced topic, and I think, again, that shows, you know, how brave you are and unfazed by the scary parts of quantum. And, you know, you didn't run away from it. So I hope it all works out, because I know maybe a little bit guilty of you ending up in a complicated business like this, because I talked about it when during COVID isolation, had some fun learning about some quantum computing and just happily sharing, oh, this is, you know, maybe fun. And then someone actually listens to your advice, which is always a scary thing. Anyway, you're not afraid of anything, and maybe, you know, doing your PhD, you learn something, and I hope, you know, that you will build on that, and I'm sure you will do well. So I think we can conclude the future is bright. Round 3 of the Dutch Astrochemistry Network is on its way, so yeah, lots of the things that you developed, we're now actually building on, you know, we're going to take the next step. We may add, you know, 1 extra atom. You showed maybe 2 extra, and even at some point there were 3 extra atoms. You know, and we are happily building on your work to go that route. Before I close, let me thank all the committee members for their efforts, their contributions to this, and also the audience for the presence here. Taha. Het gaat je goed, ik heb gezegd.
So, dear Dr. Selim, it's also my pleasure to congratulate you on behalf of the doctorate board. And I, of course, like to include your family in these congratulations. Well, all of us will get an opportunity to congratulate the young doctor when we go outside, but because we have 2 online members in the board, I would like to give Professor Leek and Professor Leroux a chance to congratulate you as well. So.
Okay, do you hear me?
Yes.
So congratulations for your work and for your award. It's a very good job you did, and I wish you the best for the future.
Yeah, thanks.
Thank you.
Yeah, let me also congratulate you. If I understand correctly, it has been a strange path towards the PhD with COVID and the end of your contract. And so I think now you can enjoy, and congratulations again.
Thank you.
So that means we are coming to the conclusion of this ceremony, and I would like to ask you all to get up. And we close the meeting with the following words. Gratias tibi agimus omnipotens Deus, pro omnibus beneficis tuis, qui vivis e regnas per omnia saeculo saeculorum.